Hello.
Oh, okay, cool. I haven't met you before, Leonardo.
Say hello, Leo.
Hello. I'm
Hi.
sorry, I'm outside, so it's quite
No.
noisy.
Yeah. Enjoy yourself.
Hello. Thank you.
Well, there's a lot of names today that I recognize names. Every once in a while, kind of showing up. It's like, oh, okay, there's a
Jose,
name.
good to see you.
Hey, how's it going, John?
Good,
How's it going,
good.
Ron?
Yeah, it's gonna be fun putting faces to names now. You see them all the time on the Facebook page.
Hope we
So I
get
don't.
plenty of attendees today. It would be
Well, I hope so. It's
marvelous.
got another minute. Hey, if we get this many, that'll be more than I expect, actually. Clyde, I gather.
Yeah, this is Clyde.
I,
I'm going to actually turn my camera off and my voice off. I'm actually having to take my car back in for something they messed up yesterday, but I'm going to be able to listen for the
no
whole
Great.
problem.
thing.
Where are you calling from?
Hey, John, Chicago.
Oh, yes, I
I
found.
I pulled over on Lakeshore Drive in the middle of rush hour, but I got
Uh,
to get back on Lakeshore Drive now.
no, I understand thoroughly. Been there. I lived there for a while, so
Oh, you got it then.
yeah,
Okay.
I used to live over by West Side Park.
On the west side of Chicago.
Well, it was West Side Park. There was an amusement park over there for years.
Oh,
That that
oh.
that was back in the 40s.
No, I was just beginning to breathe. Okay.
No
All
problem.
right.
We'll talk to you
All
later.
right. All right. Bye bye.
Vice President Harris is pinning her hopes on star power, rolling out big name celebrities in a bid to whip up enthusiasm for
Whoa.
the phase of her
Somebody needs to
campaign.
mute their mic.
Closer and closer to Election Day. Welcome to a brand new hour of the Mayor's Newsroom.
Uh,
There we
there
go.
we go.
There we go.
Whoever that was.
I think it was Clyde, but it's okay. It's all good.
Yeah, yeah. So, well, it looks like it's
It actually wasn't me, John.
Oh,
I had
wasn't it?
nothing on, but
It sounded,
I'm turning my mic off now.
as soon as your mic went off, it stopped. I thought you were listening to
It's
the radio.
interesting. There's nothing around me sounding like that. Okay.
It's all good.
somebody is.
Acoustics.
There you
Yeah,
go.
yeah.
Okay, this meeting is being recorded. Let's see. Carl, Michael. Okay. Well, okay, there's another one person coming in. Boy, a whole bunch of people from the Netherlands. Elias, how are you doing?
Hi, good,
And you're
thanks.
calling from the Netherlands as well?
No, Belgium,
Belgium, well, close enough.
very close. Yes.
You're close to my ancestors there in
Really? Ah,
in Dutch.
okay. Where they're from?
Hence my name Brandt. It's not.
Ah, yeah,
I thought early on it was German, but we found out we're Dutch.
Yes. Well, you've got another Dutch person here too, and that's Kwartjebak.
Do you know what it means?
Kwartjebak? No, I have no idea.
It's gebak means pie, and kwark is like it's a kind of yogurt. So it's kind of yogurt pie.
Oh, okay.
Cheesecake. Yeah, he says
Cheesecake.
Cheesecake.
Yes,
There you go,
cheesecake.
cheesecake. There you go.
we all love cheesecake.
Yeah, I like cheesecake, but I like different kind of cheesecake. As long as there's a girl involved, I'm very happy.
Yeah, then
Okay,
you get cheesy. Huh?
then we get cheesy. You definitely like it. All right, it sounds like we have at least a starting group right now. It'll be interesting to see how many we end up with when we're all finished here. Oh, there we go. People are starting to come in
Joining
here.
us.
Yeah, it's not as much easier when I don't have a waiting list.
Yeah, Yeah.
I just watch them kind of pop up and go, oh, okay, we have more people.
Very good. Welcome, Jacob.
Hello, how are you doing?
Good, good.
Okay. Well, today is kind of a make up for having not done this for a while. Okay, that's the best way I can put it. We used to do these things on a regular basis, and between health problems here at this end and time problems and everything else, we haven't had much time to do anything. So I want to make sure that that we get a chance to cover some of the things we're going to cover in detail in our class that we're going to be doing. But that'll be more of an extended type thing, and we'll get a lot more detail. But today is going to be more of a request type thing. We've been getting questions on and off from all kinds of different people for the last 3 months or so, and I got tired of writing the same answer over and over. So it was like, why don't we just do one of these here, and we'll just take care
Ron,
of it one time.
we've been writing the same answers over and over for the past 10, 15 years.
It's been close to it. It's been
Yeah.
close to it. What I think is interesting is it only seems to go so far that it dies out. So it's like, come on, guys, got to pass them on to the other guys too. You know, it's one of the things I like about our group is we're really trying to pass on knowledge, and unless I know it gets passed on by hearing other people repeat it to other people, then I start getting nervous because I'm getting old. I only have so many more years I can do this in. So, but yeah, so we're going to be talking about things like what is sound, you know, what makes sound. There's the old saying about, if a tree falls in the forest, does it make a sound? And, I'm just curious as to what most people here think. If a tree falls, does it make a sound? So if you guys were answering, just come on, unmute yourself and just say, yes, it makes a sound, or it doesn't make a sound. Okay.
This is really, that's a philosophical question, really, because it has to do with perception. However, what we want to discuss is this energy that we call sound.
What is sound?
And to help with the general understanding of it, in the basic physics. And if you understand the basic physics of inertia and energy conversion, etc., then it will open your world, make it help you understand.
Yeah, sound is a funny thing. Our perception of sound is really linked to our ears, and our ears are not all that great, to be honest with you. we have good ears in the fact that it keeps us from getting eaten by a lion, but that's about it. Anything past that, we're kind of like pretty deaf to the rest of the world. I mean, you got to think about it for a second. I got friends of mine who work in underwater sound, and they talk about the whales talking and the orcas talking and stuff like that, and I'm going, okay, I've never heard one of them talking to me lately, but every once in a while I keep wondering, and but you find out that they talk at these frequency ranges that are way beyond us, like dogs and cats, and I think they actually have their own language. They just don't bother to talk to us, But in any case, we're restricted to the frequency range of roughly 20 hertz to 20,000 hertz. And for all you old people out there, hertz is a new version of cycles per second. So if you see CPS floating around there, that means you're reading an old book written by people like me.
Yeah.
But hertz is we gave him credit for figuring out what CPS means.
And another thing I want to interject here is, if you look at the Fletcher-Munson curves, or in the ISO 126 2003 charts, you can see how nonlinear our hearing is.
Yeah, the Fletcher-Munson curves are kind of the key behind everything, because as a consultant, when I design rooms, large rooms especially, I try to do pretty close to an inverse Fletcher-Munson curve.
Hmm.
Because we're not very sensitive at low frequencies, and we're extremely sensitive at high frequencies. This is why you find people like me getting as old as I am complaining about, oh God, that hurts. That snare is really too loud, you know, or especially that synthesizer screaming, you know. That's because we're much more sensitive at those frequencies, and as you get older, you get more and more sensitive to those frequencies because your cilia in your ear become stiffer, and therefore they. Okay, Elias, that caught me by surprise. I have to admit. When I first saw it, I thought, a cobra. What the hell's a cobra doing there?
No, my cat is interested in your talk too. Yeah.
Yeah,
She's into acoustics.
I was sitting there looking at it going, it looks like a black cobra.
We love our pets. We love our pets.
Schrödinger's cat.
I have a big monster of a dog laying right here by me. He's just happy to pop us home.
I've chosen not to have any more pets in the last few years because I've lost too many of them over these many years. So it's like, I don't want to do that anymore. It's not fun.
Yeah.
You know, so. But in the meantime, back to our hearing, we're 20 hertz to 20K. But the other part of what we hear is how sensitive our ears are. And we really, our sensitivity is described as 0 dB to roughly 124 to 125, 126. And I want to make sure that I make that very clear as to what that means. 0 dB is a pressure of air of 20 micropascals. So your ears can detect that if you're a newborn baby. Okay, if you're older than a few hours old, sorry, you just lost that. It's not coming back anytime soon. Okay, at an age of 1 day, our sensitivity has dropped from 0 pascals to about 5 pascals, or to not pascal, to 5 dB at the low end. So that's how tight our eardrums dry out. When they dry out, they tighten up, and therefore they're not as sensitive anymore.
Just like an old microphone capsule.
Yeah, there you go. Just make sure you humidify your microphones.
I got some pretty old ones right here.
I've got repaired ones. They slice them and they dice them. They put them back in. But in the meantime, the other part of this is how loud can you hear? Well, you can hear all the way up to roughly 130, but I'm not so sure you want to, because as a general rule, if you talk to try to remember what the doctors are, Odo somethings, but in any case, they'll tell you the same thing, that at about 130 dB, about 50% of the people's eardrums will open and basically rip open at 130 decibels.
Or at least you're going to have hearing damage.
Yeah, there's two different kinds of
you know how they
damage.
do in movies these days. You know, when the action movies are going on, an explosion goes off, and then they make a ring. It's ringing because you're in the character, and his ears are ringing. And you know that's pretty apt.
Yeah.
Pretty good.
Well, an actual level that you can refer to is if you're standing next to a 747 jet 6 feet away from wind up at full power. That's about 130 decibels.
Yeah.
Okay, and you probably don't want to be there if you don't have to be there. Okay, because it actually physically hurts.
Yeah.
But I've also been to a number of Grateful Dead concerts over the years, and I've been in the first and second row, and I can tell you right now that it matches the 747 quite nicely.
Yeah.
Now I will describe something that you can hear that will actually hurt you more than that. And that is, if you ever listen to the takeoff of a Saturn V or a space shuttle or any of these new rockets that SpaceX is putting up, you're going to hear a sound of roughly 180 to 184 decibels. But you're really not going to hear the sound of it, because if you did it, it would hurt you. Okay? because what you're hearing in most cases is miles away at that point in time. But have you ever listened to a broadcast of one of these launches? You'll hear a crackling sound in the background all the time. It goes crackle, crackle, crackle. It's almost like it's just breaking up all the time. Most of us would consider it to be overdriven. Okay, well, that is really a real sound that you're hearing. Just to make you aware of what it is the pressure of the takeoff wave is at a point where it actually solidifies the air. So just think compression. You compress something, and eventually it will solidify. So imagine solidifying the air into a solid for a fraction of a second. It's almost like a pane of glass is what it is. And what happens is the pressure then shatters it. And what you're hearing is the shattering of the air. So that gives you at least an idea of what would happen to your eardrums. Not a very good thing. But that is what you're hearing. Is 184 decibels. Is you're hearing the shattering of the air is actually becoming a solid, almost like a sheet of glass. Very, very thin. But it's, people talk about the sound barrier. Well, the sound barrier in some ways is an actual real thing. It's a physical thing. And you can detect it by listening to it. So I spent a lot of time down at Canaveral and a number of the other launches because I have equipment that went to the moon and other places too. And so I got a chance to listen to these things in real life. But I was one of these real lucky people who got out there about a mile from the launch. So I had things like this on my ears. And that's why I don't hear very well anymore. Okay, too many years of hearing that kind of stuff.
Mine's from mixing loud rock and roll concerts. Oh.
Yes.
Hey guys, listen, Ron. You let us talk, and we will just go on and on and on. So everybody, ask your questions, interject, say, "Okay, I've got a question." Please, guys, hit us. Ask us the hard questions, please.
Yeah, please ask us what has been bothering you for the last 3 months that we haven't heard from anybody. Okay.
Well, my hope was in going deep into understanding what sound is, that I could maybe understand you guys a bit better. The way,
Okay.
because if I don't know if that's correct, but if I really understand how sound works, I can think more easily in acoustical framework. And I can draw conclusions maybe and be a bit creative.
Yes, sound is much different than we think it is. We've gotten so used to the simplifications that we actually think the simplifications are what actually does the sound. And that's where the biggest problem lies, because when you start thinking waves, you think, oh yeah, sound is a wave and it goes from here to here and it travels and it does this and stuff. And that couldn't be farther from the truth. Mm-hmm. It's just our simplest way we know of describing it. As you can see, the wave in my background here, it's a way of visualizing the differences in the sound. So when we talk about levels, we try to describe the sound wave as such, because that's what we're used to hearing. Is the higher it goes, the louder it is. Okay, but that's really not what's happening here. We're not going to get so deep into physics here, I'm sorry, to get beyond Newtonian physics. Okay,
well, it's basically energy. And energy can neither be created or destroyed. It's, it can be created via energy equals mass times the speed of light squared. Yeah, that's how you create energy. But when it's there, if it's in a closed system, it only can be changed to another form of energy. And if we think of that way, go, okay, well, where does the sound go when it's absorbed, et cetera, et cetera? I want to address a question asked by, I can't say your name, sir, Kawargabak. If you look at the chat, Ron, he says,
oh, there he goes. Close enough.
Okay. Yeah, sorry, man. Well, Ethan did some tests on air gaps, okay, and always thought that air gaps increase absorption over the whole spectrum. Well, what it does, it improves the absorption of the certain panel. For instance, if it has a peak at 1K, it'll raise that a little bit because there's air, it bounces, it hits the hard surface and goes back through, and it has that change due to the air, because when the energy enters the porous absorption, it will bend. When it exits, it bends again. All that is, it turns it into heat and absorption. Bounces. When it hits a surface, it loses some energy because no surface is 100% effective in reflection. So it's going to lose a little energy on the reflection and come back through. Okay, so that will, you can see a trend where it increases the absorption at the peak frequency of the absorber. However, if you close the sides, it will shift the knee point. Say it's 1 kilohertz, it'll shift it down to maybe 800, maybe 500. We have tests.
Yeah, that depends on the gap. Yeah, that depends on the gap.
Yeah, it depends on the gap.
So let's get back to what Elias was asking first, okay? Because we need to know that.
We'll talk about this in a minute.
Yes, yeah. So basically, think of an atom, okay? An atom is made up of proton, neutron, and electrons, okay? And they have different charges, okay? Ideally, if you have a real atom that is happy, it has no charge of any kind, okay? So whatever the protons are, the electrons offset it, you end up with a zero charge, okay? The point is, these charges attract each other or repel each other, depending on circumstances, two different ways. One is electromagnetically, but the other way is by gravity. And gravity is the biggest thing that we don't understand in our universe. And that is, what does gravity do? What do you need to have gravity? Well, all you need is mass. That's all you need. So if you have mass in the situation, and that consists of a proton or a neutron, as the case may be, then you have mass. So if you have let's go with a hydrogen, it's the simplest, okay? One proton, and one electron, and that's it. So you have basically a neutral atom. If you take two of them, put them together, they're going to be the same, basically, and they're going to want to stay not together. They don't like combining. Okay, that's why we have hydrogen bombs. Okay, is to make sure they get together. So in this situation here, you have two of them. But how does it talk to another one? Well, what it does basically is it sits there and vibrates in space, kind of like this vibration you have. It goes back and forth. It's called a Brownian motion. Okay, Brownian motion has a sound of roughly around minus 24 decibels. You can actually hear it. So if you guys all record, you all know what brown noise is? Everybody know what brown noise is?
Brownian noise is a noise created by heat in the resistors and the semiconductors, and it's the hiss you hear.
So what I'm asking is brown noise, just plain brown noise. We know what white noise is. We know what pink noise is. There's all kinds of colors of noise. There's green noise, and blue noise, and brown noise, and black noise, and you name it, okay? Brown noise is a very specific spectrum, and that is the spectrum of the universe. So the creation of the universe created brown noise, and that's what you hear. So when you hear the Higgs noise and stuff like that, you're going to hear kind of a low-pitched roar in the background, and it's there. You can actually physically hear it. So just remember that when you're hearing the brown noise coming at you, you're hearing the sound of creation. That is the creation of the universe that you're hearing, the echo of it. So it's a big echo for a long time. But in any case, these atoms are going to sit there and vibrate in place. And while they're vibrating as such, they're going to be transferring gravitational energy back and forth between them. Because every time one gets closer to the other or gets back closer away, you change that gravity function. Okay? So if you get one and you touch with some energy, okay, let's say, you and I speak, and we put a little pressure on this atom, it moves just ever so slightly, just a little bit more of a vibration. And in doing so, it gravitationally touches the next one. And it keeps on doing so. But neither one moves. They just stay there, and they just touch each other with a force. And that force gets transferred from this atom to that atom because of the gravitational waves.
So the energy moves.
Right. So it moves from here to the next one, etc. So are you familiar with the Newtonian cradle? You see the little balls.
Newton's cradle.
Yeah, Newton's cradle. Okay, you see all the little balls. Right. You sit there and you drop one ball, and all the other balls stand still, and then the last one moves. And that's the same as what happens to the atoms in the atmosphere. Is it sits there and clicks? It moves the energy through the atom and out the other side. There we go. One of those things. So I think in this situation, you have to think the energy goes through one atom to the next. And what it really does here is it actually moves the electron ever so slightly on the outside, and it's spinning around really fast. Okay? And when it gets to the other side, it's closer to the other one, so therefore it causes the other one on the next atom to move, keeps on doing as it spins around. So the electrons are actually what's moving the energy as they move around. They go from electron to electron to electron, and they keep doing this until such time as we hit something else. Instead of a hydrogen atom, we hit an eardrum, okay? At that point in time, right, so that, or concrete or whatever it is, the point is the electron then hits that eardrum, and the eardrum then goes, oh, okay, well, something happened there. Okay, well, you move the eardrum, eventually you move the cochlea, and eventually our brain goes, ooh, sound, okay? Right. But nowhere did the sound move physically. Okay, it just transfers energy. It's a transfer of energy. Yes. And that's the hardest thing. So when we get back to our original question, is when a tree falls, does it make the sound? Yes, it makes a sound. The question is, do we interpret it as sound? Because there's nobody to hear it. Okay, so if the brain doesn't interpret it as sound, then it's only a movement of atoms. That's all it is. Okay. So this is the same when you start thinking of sound as being atoms moving around, or at least transferring energy, then you can understand what absorption is. And absorption is the ability to take that energy from that atom and absorb some of the energy and convert it to heat. So anytime you convert anything to heat, you have done some absorption of something. You've absorbed energy and converted it from one form, which is like a kinetic energy or a moving energy, to a heat energy. Okay, and that's all absorption is. Mm-hmm. Is conversion to heat. So we lose energy by converting it to heat. And it doesn't matter what kind of absorption it is. It could be air absorption. It could be absorption of materials. It could be anything. As long as you convert it to heat, you're absorbing energy. This can be done by friction. So if you have fiberglass and you run air through the fiberglass, it's going to, the atoms and molecules are going to hit that fiberglass and slow down because it's physical. It gets in the way. Okay, so it slows it down. And every time it slows it down, it converts some of that energy of the sound into heat. Therefore, that is how fiberglass absorbs sound, is through friction. Okay, just like you going through water. If you're trying to swim through water, you'll notice you have a tendency to slow down a little bit as you kind of move forward. It's like it takes a lot of effort. You got to work your shoulders. That's because you're trying to go through a medium that is absorbing your energy in the matter of heat. That's why you're tired. At the end of it, your heart's going pump, 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 pump.
It's inertia, and you're moving a liquid or a gas
through it.
Or a solid, through it. And it will.
Yeah, it's a solid going through a solid of some kind. Okay, and you got to think of everything as being a solid at some point in life. including air, because to vacuum, air is solid. Okay, that's the best way I can put it. But that's one way of absorbing. There's another way of absorbing, and that's called diaphragmatic action. And all you have to do here now is think about the drum head of a drum. Okay, you take a drum head and you hit it, it bends. Okay, where it bends, and by the way, in a drum head, where is it bending? It's not bending in the center. Okay, that's the easy answer. Think about it. It goes all the way to the outside edges, and then there's an outside edge which is pinched in place, and that doesn't move. So therefore, if you got something that's wanting to move the whole thing, it's bending just a fraction of an inch outside that hold point. So you have a circle of bending around the head. Okay, that bending action is a movement of atoms against other atoms. You're moving them against each other, and you have a friction. But the bending actually causes heat. So the way you can tell this is take a piece of metal and just bend it back and forth.
That's why drum heads wear out.
Yes. So if you bend it back and forth, that bend point gets hot. And if it gets hot, that is heat, and that is absorption. That action of bending is an absorptive function.
Energy conversion.
Right. So you've done that. A third method is what we're familiar with, and that's called resonance. Okay. And you hear that in an organ tube, or you'll also find that in a shock absorber. Okay. So if you take air and you compress it very rapidly like this, okay, the air in between gets pressed and it gets denser and denser and denser. And if you do it hard enough, you form a solid, and that's what happens with a rocket engine taking off. Okay, but in the meantime, it gets hot. How many of you ever taken a shock absorber and moved it inside and out like this a few times and feel how hot that tube is?
Or a bicycle pump.
Yeah, bicycle pump the same way. Okay, you're heating up the air inside that thing by compressing it. Okay, that air is going, no, I don't want to get close to the other thing. I'm going to give off heat, make it go away. Okay, that heat is absorption. So a pipe organ has a column of air that has a little plug that goes back and forth, and it reverberates before the mouth and the plug over and over, back and forth, depending on frequency. And every time it moves back and forth, it compresses the air in that tube, and that tube gets warm. So if you get an organ pipe, you can feel how warm it gets. So air can compress liquids. That's why we have shock absorbers. We use hydraulic liquid. Same thing. It works the same way. Okay, but that is heat, and that's a conversion again. So if you have a really good car and you're going out dune buggy, you're going to hit a lot of bumps and stuff, and those shocks are really going to let you know it, and they're going to be very hot, and that's because they've absorbed all that moving energy.
That energy
and converted
from the wheels.
Right. Moving up and down. So now you have that. So these are the ones we're familiar with. This is what we've known for the last 100 years. These three methods of absorption. Okay. The research that we did about 9 years ago on edge effect showed that there is another form of absorption. And we've got plenty of measurements to show what it does and stuff. And that's diffraction. So if you have a diffractive edge, an edge of a sharp edge of anything, it doesn't matter. It could be a piece of wood, it could be a piece of metal, it could be glass, it could be, you name it, okay? But the point is, the bending of energy as it goes past an edge, okay, is the same as bending the energy on a diaphragm, only you're doing it in air. So therefore, it works the same as diaphragmatic, except there is no diaphragm. All there is air movement, okay? And this was shown back in the 1950s with radar. People say, well, what's radar got to do with sound? It works the same. Don't worry, it works the same. It's just, it's just a lot more energy. You can see the change in the temperature around that edge because the wave was 35 megawatts. Okay, we can measure that. Okay, you can't measure it in sound because there's not very much real energy there, but we can assume it works basically the same in physics. So in this situation, we're able to measure it. We can figure out what the percentages of bending were. But what we discovered was that if you have a straight edge, just okay, maybe I'll describe it this way. Think of a point in space, just a single point. If you hit it with energy, the energy will hit that point and scatter in all 360 degrees. Okay? That's the energy. It's going to get lost. We're going to lose energy that way. Now, if you take that point and if you extend it in space in one direction, you now have a line. That line, if you hit it with energy, it will deflect energy, but it will deflect it basically along the length of it. So if you hit it coming in on an angle, say 45 degrees to an angle, coming in on a long thing, it's going to come off that line perpendicular to the line, always normal to the line. So if you take any angle coming in, no matter what angle it is, and hit that line, it will come off that line in the opposite direction, perpendicular to the line, period, no matter what happens. Okay? That means that you're bending that energy from any angle coming in, random angle, to a single line coming out. This means you're putting all your energy and you're forming coherent energy. This is basically the same as a laser. Okay, all that light becomes coherent energy. So we're now gonna make all that sound energy coherent coming off that line in that direction. Okay, and it's gonna come off around the line 360 degrees, but it will be coming out from the line as a center and exploding outward, kind of like a star. Feel your cross section. Okay, now if you take that line and you extend it 90 degrees or any direction from the line, okay, and form a plane. Now you're going to be looking at what does the plane do? Well, if the sound hits the edge of it, it's going to come off that energy perpendicular at basically anywhere between here and here. Okay? You can see the energy of the plane here is my hand. And we're going to hit it on the edge, and then we're going to come off, and we're going to bend all the way down and all the way up. Okay? Now, let's take this plane and let's give it a third dimension, thickness. And we're going to build this wall like this. Okay? Now, if the sound comes and hits this energy, there is a plane here as well. There's an edge here, but then you have a plane attached to that edge, going 90 degrees to the first one. Okay? That means that all the sound that would deflect downward is not going to happen. Okay, because that plane's going to keep that from happening. So what's going to happen is, as a rule, it will sit there and bend 45 degrees. So half of that angle, whatever that angle is of the edge, okay, the sound is going to go 45 degrees to that. Period. That's just mathematical. So it's not going to go up. It's not going to go behind anymore. It's going to just follow that edge, and it's going to reflect off, and you're going to end up with a 45-degree reflection along that face. Okay, so now you've done something to the sound that the sound really is kind of getting a little angry about it. You've made it very coherent, and it has one direction. And in doing this, you're going to bend the air and absorb sound like crazy. So now that edge becomes absorptive. And this is what we call by edge effect. Is we can actually calculate how much sound gets absorbed, what the equivalent absorption is, etc. And there's a series of papers out there that were just published on how to use absorption in small pieces in your studios. So contrary to what everybody thinks, more absorption panels does not mean more absorption. That goes against everything we've learned for the last 100 years. Is, you want panels that cover all the walls and just suck up the sound. That's not really true. You're wasting your money and wasting your time, both. And there's something you're going to find out about me is I hate wasting money. Okay, because I work too damn hard to get it. So I want the maximum effect that I can get with my money. And what I have found and what we've discovered, there's some papers, again, you can ask me, I'll be happy to give them to you. They're going to go on my website here probably the next month or so. Just depends on how soon I get back to my website again. But these are papers that were just published within the last month and a half. Dr. John, I gotta remember. in Australia.
Davis?
Yeah, yeah, Davy, John Davy.
John Davis, yeah.
Yeah, John Davy. So John Davy published the papers, and the reason you'll see him as the #1 author now is because I'm too damn lazy to write papers. I'm too tired to write papers. Okay, I haven't got time to do it anymore, and I don't really have the desire to do it anymore. But I will be happy to work with somebody like John Davy, who's a professor at the University of Victoria in Australia, and he has written the papers based on our research. You know, and that's fine with me. I'm happy as long as the idea gets out there. I'm quite happy with that. So these papers are written by John Davy, myself, and Bob Hallman, who is used to be the head scientist for Armstrong Corporation. And what these do is these explain how you can use small patches of absorption and space them correctly. And in doing so, you can double or triple the absorption. So if you have, let's say, a checkerboard shape on your wall, and instead of having checkerboard where you have corner to corner, which is what most people do, space them out the same distance. So if you have a 2 foot by 2 foot piece, then make sure you have a 2 foot space on all sides of it as well, and then put the next checkerboard. So it's a 2 foot spot, and then another 2 foot spot, 2 foot apart in all directions. If you do that, you will maximize your absorption to about 1.7 times what you had originally. Yeah, I know. It's scary. We've tested fiberglass FR705, which, you know, you see a lot of stuff out there. It's kind of yellow stuff that's out there. It's 6 pound density. If you look at a 2 foot by 2 foot
kilos per cubic meter. Same.
There you go. See, John speaks all that. But in any case, the point is, if you test a monolithic piece of this, it will give you an average absorption coefficient of around 0.8, 0.85 at around 1K, which is, you know, a fairly decent absorption coefficient if it was a real coefficient. But if you take it, you space it like we're talking about, and you start spacing it with space and stuff, if you extend that space out to that same size, you can take that same frequency and move the coefficient to 1.7 or 1.8. And that's over double. And people say, well, is that a real absorption? Well, yeah. I mean, that's how you got that number. Okay.
It's from the diffraction, edge diffraction.
Right. Yeah. The real point is, you know, what you're doing is you're taking the absorption characteristic of it and dividing it by the area, which is the old way of doing it. What that really tells you is that the area is not the only thing that affects absorption.
Right.
Okay.
I have clients that ask me about, well, what about panels on the doors? I said, well, you just got absorption here and here. The door disappears as a reflective surface.
Yeah. This is the other thing that people don't understand is all this space in between, the 2 foot space in between, it's not going to give you a reflective surface. It actually acts like an absorptive surface, just like the material itself is. So basically, you double the amount of surface area you have with half the material. So, and I think that's the key to remember. So you can treat a room for half the price and get the same effect as you would be if you put panels on all the walls.
I still like to cover my walls, though.
Do it with cloth. It looks the same then.
we could try that. We could try that in future design.
Yeah.
But the space is lost anyway.
Yeah, the space is lost no matter what. So you can either take what Mother Nature gives you, which is a whole bunch of extra absorption, or you can cover it and just drive your cost up double and make everybody else happy. You got something for nothing. It's it's called the ladies in the church. Okay, they like a certain look.
Yeah.
Okay,
Yeah.
and it doesn't matter whether it works or not. They just want it to look a certain way. So
Yeah.
my suggestion is you make it look like they want it to look like, but you do it the way you want to do it. Okay, and that's how to keep everybody happy. My job as a consultant, both in small rooms and large rooms, is to make everybody equally unhappy.
That's right.
Okay, if you can't make everyone equally unhappy, you have not done your job. Okay, so just be aware that that's the whole idea behind our whole job. If you're a recording engineer, yeah, you're going to make everybody equally unhappy. The musicians are going to say, "Oh, we could have done a better job here." The singer's going to say something else, and the technician's going to say something else, and the producers are going to go, "I want it this way better." Okay, when they're all about equally unhappy, you have done your job. Okay, and that means you got a record that'll probably sell as well. And by the way, I can vouch for that. I have a million sellers as well. Okay, it's one of these things where you look at it, listen to it, and go, "Huh? How'd you do that? You mean make a million seller out of it?" I made it so everybody out there was equally unhappy, and a lot of people bought it for that reason. So, but in the meantime, so that at least answers the question of what edge effect is.
It relates to my studio question that I have, is how to determine what is a good balance between absorption, reflection, and diffusion in a listening room. How do you determine this balance?
Well, you use absorption to get your average room, I would call it room curve, down to a reverb time that is within what you're looking for. In other words, let's say you want an 8/10 average absorption. Okay, you want to make that 8/10 consistent from basically 250 hertz all the way up to roughly 4K. Okay, so you're going to put enough absorption in there to bring that curve down there. Okay, and you can calculate it any way you want to. My suggestion is use our method. It'll save you material, but you still have to do it. Okay.
I have a formula in my room mode calculator.
Yeah. Yeah.
And it predicts what your decay should be. I don't call it RT60, but it's
right.
A decay in the room. Usually in small rooms, it ends up being pretty damn tight. However, if you place diffraction and phase change units in the right positions, you can have a sense of space in there, and it feels like a normal room, and it'll feel good, and you'll be able to hear everything clearly without the distraction of these hard reflections.
Well, let's talk about a very specific diffractor, absorber, what do you want to call it? Everybody's familiar with RPGs. Little holes everywhere.
Are you talking about the 2D diffusers, the blocks?
No, it's a flat plate with little holes drilled in.
Binary amplitude.
Oh yeah, okay.
diffusion.
There you go, BAD panel.
Yeah.
Binary amplitude. Okay. Does the binary amplitude panel work? There is an answer in acoustics that we all know, and you hear it from other people too. It all depends. Okay, that all depends covers a lot of crap. Okay, so you got to be aware of it. Okay, but in this case of a BAD panel, it all depends. We've measured it for scattering, which using the old ISO standard. Okay, I don't know how many of you people understand scattering or not, but I will tell you this: the ISO standard for scattering is useless. We were the first laboratory to be able to do it full scale. And we actually thought we had measurements, okay? We actually thought we did, okay? And we're like anybody else, here's the thing, we got an answer, and all of a sudden we're looking at an answer, and there's a chart. It's like, okay, yeah, we got an answer, okay, based upon that standard. What we didn't take into account was the standard itself could be wrong. Because it's a standard. If it's standard, it's got to be right, okay? One of the things I've learned in working in standards is that standards are often not right. What standards are is something that we all agree on can be equally wrong. As long as we all agree on that. Okay? We don't care whether it's right or wrong. What we care about is, do we get the same answer? Okay? And take my word for it, the first 5 years of working in standards, as a scientist, I really had a real problem. Okay? Because as a scientist, I'm always looking for the truth. As a standards person, I'm not looking for the truth. I'm looking for what we can all agree on. Okay? And it may or may not be the truth, as long as we all get the same answer, doing it the same way. And that's what standards are. So standards can be updated as we learn. Take my word for it. I got people that they looked at me funny. I kept saying, guys, we're here in standards committee. We're all scientists. Don't we want the right answer? And everybody looked at me and said, well, we're not all scientists, number one. Half of us are users. Half of us are manufacturers. All we're interested in doing is getting the same answer so we can test it the same way and get the same answer. And I'm looking at him going, so the wrong answer is fine. Yeah, as long as we can all do it the same way, then we're okay. So that's how the absorption test came to be. Well, it's the same way the ISO test as well. The ISO test for scattering was a test where we went into a reverberation room. We put a material in the reverberation room on a turntable, and we measured the absorption while it's standing still. And then we measured the excess energy by what was left from the absorption to the total energy in the room, reverberation in the room. So we assumed that if you absorb the sound, a certain amount of energy would disappear, just like it does in an absorption test. Okay? But we also said that if you move it then and rotate it, as it continuously rotates, then all these reflections, all these phase differences that were showing up because of the holes would eventually cancel each other out, and especially if it was random, and therefore you'd lose energy since it's canceled out, therefore we could measure that. Okay? And that's what scattering is whatever energy is left over after we subtract the speculative energy from the regular energy. And that's what the ideal was. The only problem nobody thought about when they did this was the original research was done in a free field. And in free field, you can see a phase differential between reflections. Okay, so if you take a reflection and you look at it and you turn it and it changes it, you can see the phase difference. You can actually read it. Okay, but what nobody took into account was that in a reverberation room, what is the definition of a reverberation room? And that is equal energy at all energies, at all frequencies, and equally random phase.
Mixed phase. Yes, sir.
Mixed phase. So if you have mixed magnitude, you have mixed phase as well. And if you have mixed phase, how can you separate each phase from the other so you can subtract it?
Right.
And we found that out by accident. We did our original measurements in another reverberation room that was around 250 cubic meters, and we actually got actual results that we could see. And that's because that reverberation room was not fully reverberant. It was not big enough. When we opened our new place, we went from 250 cubic meters to almost 800 cubic meters. And all of a sudden, we have a real reverberation room that has a space inside of it that is completely and utterly random. You can actually go and measure it. You can actually put a meter in there and measure everything. And when you actually measure the impulse responses, you find out that there is no phase differential either because it's random in that center. And all of a sudden, the answers you were getting for the standard were completely and utterly random. It just depended on each measure. You can sit there and run the measurement 10 times, and you got 10 different answers. And pretty soon it was like, well, I wonder why that's happening. It's the same sample, it's the same equipment, it's the same software, the same everything except the room. But why are they random? And the other one you go and you get a real answer. Well, we got down and started thinking about it, started talking about what is a reverberation room, and that's what we figured out is that, it wasn't reverberant enough. Okay, so now we've kind of figured out that what scattering is a function of the edge effect. That edge effect is the scattering function. That is the scattering function, and we can detect how much of it is based upon the calculations of what we've been able to do. So in any case, the point here is that the diffusion or diffraction around the edges allows us to increase the absorption in doing this. Therefore, when you look at all these programs like Ease or Odeon or Cat Acoustic, where they tell you to please put in a scattering function to compensate for the reverberation time, that is taken into account by putting a correct absorption coefficient. So absorption coefficients are limited in these programs to 0.999999. Okay, 1.0 doesn't exist in absorption. That is an open window. No, I hate to tell you, it's not. Okay, because we can measure things up to 1.9, 2.0. I've actually measured absorption as high as 2.3. So if you use that number, that takes into account and adds all the diffusion characteristics into it, and you end up with the same amount of absorption in the room. So you have to do this by hand. There's no programs to do this yet. There will be as soon as there's an official standard for diffusion measurement.
Yes.
But nobody wants to do anything on changing their programs until they have somebody to blame for it. Okay, you have to have somebody to blame. So it's called CYA. But in any case, this is how you can do that. You can do this by doing it by hand and doing this other thing. So in any case, this is another form of absorption, and we need to take that into account. So that takes the place of the scattering coefficient. Okay.
I put some links in the chat for your papers, Ron,
Oh,
on your site.
great.
I have
Okay.
quite a few of them listed on my resources page as well. So
Yeah.
feel
And
free.
and if you ever want to just go searching, you can go to my website, which is nwaalabs.com, and go to the front page, and there's a link there to all the papers I published up until the last 2 years. The last 2 years, I have not put any papers up there yet. Those, I was COVID. Everybody else is COVID. Nothing was happening. So these last two papers I have not put up there yet. They'll go up there in the next month or so. So it depends on how fast I get a chance to get back to my website.
Yeah.
All right. But other than that, they should be all there, all the things on scattering as well as absorption. Now, John was talking earlier about the gap, and a number of people in our industry over the years. If you go to the YouTube and look at acoustics and listen to people talking, I would say about 90% of it is wrong. Okay, especially Wikipedia. Please do not go to Wikipedia and listen to anything it has to say on it. I've gone in there a number of times and updated things that have been wrong, and the next day I come back and it's back
They're
being
all
wrong
changed
again.
back. Yeah.
Okay,
Ridiculous.
and this is because people can't understand that sometimes what they learned is not correct. It's like, I learned it, it's in the book, it's got to be right. Well, it's kind of like, oh yes, it's on the computer, it must be right. Okay.
One of the primary errors is the thought that the absorption coefficient is a percentage.
Yeah. Yeah, I have people come to me and say, it's 0.9, 90%. No, it's 0.9. That has nothing to do with percentage.
Right.
It is just it is a number based upon dividing a number of sabins by a number of square feet. And that's only three numbers involved here. You've got total absorption coefficient, okay, is equal to absorption divided by area. So if the limit on a coefficient is 1 and the answer is more than 1, then obviously one of those other two numbers is wrong.
Mm-hmm.
Okay, I mean, it's just simple mathematics here. Okay, you know, you don't have to be an algebraic person. You don't have to be a wonderful mathematician. All you have to do is be able to divide one number by another. And if you do that and the answer is wrong, then obviously one of those two numbers is wrong. Okay, and we pretty much know that the absorption number is as correct as we're going to get. That doesn't mean it's correct. It just says it's correct as we're going to get. Okay, and that's based upon deriving it from the difference in the time of a decay in that room. That's it. It's all it is, a derivation. Okay.
And we don't measure absorption directly. We measure how this whatever we put into the room, how it moves the room. That's all we can do. We can't, so that's how we develop the absorption coefficient and all these measurement techniques.
Right. So what's happened here is since the absorption is correct, then obviously the divider, which is the area of the sample, is incorrect. So therefore, the sample itself doesn't have all the information that's necessary in order to be able to figure out what that absorption is. And that's when we get into this edge effect and the perimeter length and all the other stuff. Okay, and you can read more about that in my papers.
Yeah, read his papers because it explains this, and
right.
It's like, oh my God, really? Wow. You go, how can that be? But look at the data.
The data's there. Yeah, data doesn't lie. But in any case, the point is it's there. But there's a lot of other people out there saying things like, well, if you put an airspace behind it the same size or the same thickness as the material, you're going to double the absorption. Or you're going to increase the absorption by a substantial amount. And like everything else in our industry, it all depends. Can you get increased absorption? Under certain conditions, you can. But you have to meet those conditions. If you don't meet those conditions, no, it doesn't happen. Okay? So let's, and that's the problem. People hear something and they assume that because we said space behind, any space behind anything equals more absorption. It's called running with the fact and then trying to add on to it.
Yeah. I always keep saying acoustics is counterintuitive. And if you say, well, then, and you go off.
Yeah. Everybody tries to run with something. It's like, here's the fact. Now let's expand it in all possible directions, and it should do the same thing everywhere.
Yeah.
That's not necessarily true. Physics doesn't care. So in this case here, if you increase the gap, it will increase the absorption, but only under certain conditions. And you better get those conditions right, because otherwise you're wasting your time. So let's talk about the gap here a little bit. Let's talk about the most used material out there, and that is FR705. That's Owens Corning 6-pound density fiberglass. Okay, I know the rest of the world can't always get it, but there's other equivalents out there. Knauf has them, and a lot of other companies have that same equivalent out there. And if nothing else, you can always contact somebody in the U.S. and send it to you. Okay, and either way, the point is you can get it if you want to. But let's assume the typical panel, which is 2 inches thick. Okay, people do 1 inch, they do 2 inches, they do 3 inches, they do it 4. Let's just settle on 2 inches for our discussion here. Okay, this means that supposedly, according to people like write this up, if you put a 2-inch airspace behind it, you will double the absorption. No. Okay, that's all I can tell you. Is I was a consultant for almost 50 years. Okay, and I can tell you that as a consultant, I believed all this stuff because that's how I learned too. I learned from the books, from you name it. All these guys out there writing all these books about sound and acoustics. Okay, Baranek. I read all of his books. I read all the other books from all these other guys telling me how I could build things. And being a typical dummy scientist, I just assumed they were right. Okay, that was until I started calculating rooms, and then going, well, the calculation says you should do this, and yeah, you can build it this way and do this and do that. They'd go up there and put it up, and then I go measure the room, and the measure. It's like sometimes the room would be great, and other times it would be like, oh yeah, you're in deep crap. Okay, because now they're going to sue you because it's going to be wrong. Okay, and it's surprising how often you can be wrong before you go, I did it the same way. The answer is different. I just don't understand why it's right this time and why it's wrong this time. And then you start questioning yourself. Do I really know what I'm doing? You know, and after a while, you start getting older and go, I don't care anymore. Okay, I'm too old to worry about it. But the point is, you start questioning yourself, and anytime you start questioning yourself as a scientist, you know that makes a real problem. Well, I told some of my friends, they told me I should open a laboratory, and I said, you never want to give a consultant his own laboratory, okay? Because now I have the ability to check all these questions that I've had for years and years and years without depending on other people to do it. You know, and it's kind of like, okay, are you gonna make a lot of money testing things? No, I'm probably gonna spend a whole lot of time doing nothing but what I want to do. Okay, which means I'm gonna be poorer than I was earlier. Okay, which is part of having a laboratory. You know, but the point was, I sat there and I thought, okay, they tell me I can take these panels, so I tested. I put it on the floor. I did an A mount, and I tested. I came up with a nice curve, and then I put it on 1-inch battens and put a couple sticks on either edge of it, and put it up in the air 1 inch, and I tested it, and came up with another answer, and then I put it on 2-inch battens, and then I put it on 4-inch battens, and I put it on 6-inch battens, and I got answers each time, and it didn't quite match up with what theory said. Okay, theory said if you increase it every time you increase it space-wise, you should get more absorption. And what I found was after 1 inch, the absorption went away. And it was like, oh, okay, because I checked it at 1 inch, 2 inch, 4 inch, 3 inch, etc., and all things. But every time I tested it, at 1 inch, I got a nice bump. When I got to 1.5 inches, the bump started going down. At 2 inches, it was gone. And it was like, oh, okay, that's not what I expected. Okay. It says that I should get more. So I said, well, maybe it has to do with 4-inch material. If I go 4-inch material, 4 inches should give me the same bump. Well, I put 4-inch material down on the thing, and I put it up 1 inch. I got a bump. And at 2 inches, the bump went away. And it was like, okay, that's not what they tell me it's supposed to do. So I tried it at 6 inches, and I tried it at all kinds of different thicknesses. And what I found is as long as the edge is open underneath, in other words, you have an open, you can see underneath the panel, the sound will increase the low frequency just slightly with 1 inch. Anything beyond 1 inch, it goes away completely and utterly. So the question is, why did that happen? And being typical scientist, I went, well, there's got to be some reason, because, you know, things don't happen just because. Okay? So what I ended up doing was putting in a sensor that could detect air movement. And I put right near the edge of the panel, see what would happen. And what I found was that when you had 1 inch or under, the air coming through the front of it would pressurize the air behind it, that gap. Just from, you know, basically like if you think of a sound front, it would pressurize it, okay? Just like you would in a box, okay? And by pressurizing it, the air would escape from the edges, being under pressure. So, I mean, there's an opening there, why not? Just go there, right? So just visualize, you know, air going down and out, okay? I can detect an air movement up to 1 inch. So I could see that air was under pressure, and it was escaping the pressure by escaping to the outside edges. When I went to 2 inches, there was no longer air movement. And that's because the amount of square inches of empty area was enough to relieve the pressure in that gap between that 1 inch. And as long as there was no stopping the air, there was no reason for it to increase the absorption. Okay? So that told me right off the top that 1 inch airspace is the maximum that you can have on any panel that has an open edge. So if you put them on little blocks, you put them on the wall, if you go beyond 1 inch, you're wasting time. In fact, you're losing some. Now, what does happen in our testing, we have something called an E400 test. And the E400 test covers the edges all the way between the flat surface and the material, top edge. So in the E400, what you end up with is a panel, and you have 400 millimeters of airspace behind it, and it's completely covered all the way around, so there's a wooden border all the way around that covers everything and is sealed to the floor. Therefore, this airspace underneath the panel is now trapped. It doesn't have any place to go. And it's like a piston. If you apply pressure on the front, it will increase the pressure underneath. And it will continue to do so as that wave front moves towards the ground. And therefore, it compresses that air. And it continues to do so until it stops. Okay, then it bounces. Comes back the other way. Okay, what we found was when you have that kind of a situation, it continually increases the low frequency response until it stops. At that point, it bounces, and you get another bounce on that direction, so you get an additional push of another 0.3. So the absorption almost doubles, and then another 0.3 added to the bounce. So therefore, if you want to increase the low frequency absorption of your panels, make sure you surround your panels with something hard so that it basically seals the air in. So and make sure they're sealed. Don't just put them up against the edge and say, well, it's close enough. It's not. As long as there's air that can move, it will relieve. So seal it with some, silicon sealer or some mastic or anything else like that. But if you do that and you seal these edges all the way around, then all of a sudden this becomes a big piston and absorbs sound.
So you not only get the porous absorption, you get the pressure absorption as well.
Right. So nothing like getting something for nothing. Okay. And that's what we look at. So think of it this way: it's just another way of you do a dual absorber, you do a piston absorber, and you do a porous absorber as well. Okay. Now there is another way of doing this too. I just had it in my mind and it just went blank. I hate that. When you get too old, everything goes blank. And by the way, you can tell how old you get by how much of it goes blank. It's like, ooh, yes, I was thinking. I went into this room for some reason. Now, what did I go in this room for? I can't remember anymore. But in any case, the point here is that, you get a lot of absorption that way. Now, this is what it was. How many of you use Q-type diffusers?
The Schroeder type?
Quadratic. Yeah, quadratic.
Yeah, the Schroeder, the Wells.
The slats. You see the slats, vertical slats?
Yes.
Anybody ever used these on the wall, back wall or front wall or anything? No? Okay, I don't see anybody raising their hands.
The original RPGs, that you see in the back of LEDE rooms or RZ rooms.
John, you have a picture of a QRD?
I'd have to dig it up.
I know you will.
Let me dig.
I will too. But in any case, they're just vertical slots. Okay, different things. Okay, and the point is they'll tell you that all these things have a lot of absorption to them as well, and that's not because of the material. The material's hard. Okay, so it has to do with the functioning of the QRDs. Now the question is, how do they absorb? And how many of you ever used cityscape diffusers? See little squares that are like little square blocks, and they put them in and out like this. It makes it like a checkerboard that's moving around in 3D.
A skyline.
Yeah, skyline.
That.
Skyline is another name for it. Okay, They work somewhat the same way, but they don't work like you think they do, and they don't work nearly as well as you think they do either. And how can we tell this? Well, we've developed a method of measuring diffusers using the same method we use for measuring speakers. Now, how many of you have ever used a speaker directivity balloon? You find in ease, you put them into a program and you end up with a beautiful balloon, looks like a flower. and it's a speaker. Okay, we can measure speakers that way by just putting them out there and then measure what the attenuation is at any point. Okay, well, we can do the same
the
thing.
chart you get on a microphone with
Right.
the here and the sensitivities
Yeah.
and different frequencies.
But think of a three-dimensional chart instead of a one-dimensional. Okay,
Mhm.
so we do the same thing with speakers. We do the same thing with diffusers. So John was saying something about, we can't measure absorption directly. That is not necessarily true anymore. And this is one of the changes that's occurred in our industry.
With the free field.
Okay. Right. If you go to free field and you bombard the surface of the diffuser with a speaker, and first thing you have to do is determine what normal is for that diffuser at its surface. Okay? So the way you do that is you put a flat plane right at the surface of the diffuser, and you put a microphone on it with a boundary measurement process. Okay, what's the name, John?
I can't think of it.
I know, the same way.
Yeah, use boundary microphone or
Yeah.
PMZ.
Yeah, right. Any of those things where
Pressure
you have
zone
that
mic. Yeah.
Right. Pressure zone
PZM.
mic or a regular mic by putting the tip of it and putting the fiberglass there instead of the whole thing. Okay. In any case, we can measure the frequency response of the speaker at that point. Okay. If you do that, then you can put that into software programs and normalize that. So basically, it becomes a flat line at that point in time. Okay. If you do that and you include the normalization curve, then if you measure a diffuser, then any attenuation you have can be referenced to that normalization.
Mhm.
And therefore, the difference will be what the balloon is. So whatever the difference is between the normalized point and that other point. So each frequency can be measured, normalized to that point. Okay?
You see the
You're doing
attenuation
that-
at each frequency and at certain distances and different
Right.
Angles of dispersion.
Right. So when you look at the entire balloon, the entire cut across, and tell you how many dB it is reduced, what the attenuation is at that point, at that distance, okay? And we can tell you how far you are and what the attenuation is. If you can look at the attenuation and say it's down 3 dB at a distance of 6 feet, okay, then you can calculate the amount of absorption there is. It's funny how that works. So this is another way of measuring. So what we are in the process of doing, and John is delightfully paying to do this because I have to make a living too, okay, is we're measuring the absorption characteristics of all these materials like 705, etc. And we're doing it both in a monolithic and a poly type situation. So we have the whole spread of absorption based upon the amount of savings, okay? We're also taking the same material and we're going to put it on the diffuser board and measure it in a free field. And we're going to tell you what the coverage pattern is and what the attenuation is. And between that, we should be able to reference an attenuation to a certain amount of savings loss.
Yes.
And in doing so, then we're going to be able to tell you all the other things you need to know about absorption, including angular absorption.
Yeah, that's the paper.
Yep, that's one of our papers coming up. So you can be aware it's coming. Okay, but these are the kind of things that we do in our situation. And so when you hear us talking about some of this stuff, a lot of times we're telling you what the bleeding edge of our industry is. Now, you can choose to believe it or not because it doesn't always match up with the books, but that's the way it goes because we always write new books. Okay, so I think
Science is only beaten by better science.
Yep.
Always, that's the way, yeah.
Mark, you have a question?
Mike,
You popped up.
turn your mic on.
Yeah, I'm just putting on. Hey, how are you?
Good.
Thank you so much both for doing this first. I appreciate you guys sharing your education experience. So obviously it's a long-term learning process for all of us, but for someone, it's not to undercut all the detail you guys have, But for someone, I'm in a rented space, I've got a small room and I just want to get tracking. So like obviously making a build at some point when I own my place next year would be great, but for just working, what would you start with? I know treatment's key to just making it usable, but just for tracking vocals and guitar in a small space, it's 8 feet, but it's like 16 feet to this wall. And then
Sure.
there's where the door is, like to just get started, like
Right.
obviously I'm on board with you, Ron, about saving money. And then obviously I want to make it good, but it's a
Right.
short thing. It can be custom. So what would you
In this case, John has many sheets of Excel that will tell you what the decay time should be for that volume of a room
Yeah.
to be able to
And
do
you
these
don't-
things.
Now, the room mode calculator that I have programmed, it's mainly for a mixing room or a critical listening room, okay? And so that decay figure. You can bump that a little bit for a tracking room. The thing is about tracking rooms, you don't want them dead. And you definitely don't want them live. You know, people call them live rooms. It's I always like to say that it's called a live room because that's where live performance occurs. But you need to have, unless you're just tracking one instrument at a time, you know, it can be pretty tight. But to get the spacious sound, you need lots of diffraction. You also need plenty of absorption so you can have fall off from one mic to the next. So you can track things at the same time and use a compressor on this mic, and it's not going to bring the other instrument up in that mic so much because you have enough trapping to control the fall off.
And when you talk about, obviously there's a different types of trapping and absorbing, you just use like broadband absorbers, like 8-inch ones, just put those in the space and then above on the ceiling.
If you need the bump from 70 hertz to 500 that Owens Corning Pink will give you, that's that lightweight fiberglass, which currently we're doing tests now to determine, because all the data that I've seen is that rock wool performs inferior to glass wool, but we're still working on tests to determine where these cutoffs are.
Yeah.
But
so you're aware, John's paying for a whole series of tests that we've been at the laboratory stripping 11 years worth of absorbers because we got panels at different sizes, different materials with nice, beautiful fabric on them and stuff, ready to hang and stuff. And I'm ripping off every bit of it till we get down to the stuff inside. And that way we can stack it in so many different ways and get you 8 inches or 10 inches and tell you exactly what the differences are.
compare density to density.
Right. So we hope that we'll have that in the next couple of weeks or so. I would have it immediately, gentlemen, but I was in the hospital yesterday. I will be in the hospital a week from today, getting my heart work done, because otherwise I won't be here. Okay. So I have to wait until I recover. Yeah, so I have to recover about a week or so before I start the test. So it'll be probably about the middle of November before we do all this series of tests. And then we'll give you more information and stuff.
Yeah. But Mark, to answer your question about a tracking space, okay?
Yep.
As we were discussing earlier about checkerboarding panels, being economical and efficient with the absorption that you place, if you space them, you know, panel, wall, that kind of thing could do marvelous. However, remember that when you're spacing it, that wall in between them tends to disappear as an absorptive surface. Okay, so you're not going to get reflections from those surfaces. So you need to add in diffraction and diffusion so you have a sense of space in there. So it sounds like, you know, you're playing or you're working with your other artists, and you're working off of each other, because when you're sitting in a tracking room, it's a creative space, and you got to be able to hear each other and groove. You could invite the muse in to work with you. And
just two follow-up questions. Like one, when I've got this little nook in the corner here. Like, would you just ignore that as if it's negligible when we're doing, like, putting in the measurements for the room, like length, because it's like 19 feet to here and 15 feet 8 to here. Like,
measure to 15 feet, because that's the main portion. That's your largest surface. That's what I do. In that entryway, you may want to run some impulse measurements on that entryway and see what kind of resonances you get in there, and maybe a panel on the side or on the ceiling or something will just take care of that. So you don't
Yeah,
want
Mark, I where do I go with this?
yeah.
John and I have very different specialties. I specialize in large rooms like opera houses
Yeah.
and concert halls and stuff like that. That's what I've been doing for years. I don't do very many small rooms, although I have done a number of them over the years that have been very successful. What I would recommend to you would be to hang a velvet curtain. Go to a place that has theater.
That'll take care of it. That's perfect. Yeah.
Take a velvet curtain and put it across that opening.
Yeah.
Done.
Okay. Or if you really want to do something good, just put it across the entire back wall.
Okay. Yeah.
Okay. That will
And
take.
just for the, and sorry, just follow up for the panels. Like, just instead of like limp bags and worrying about that stuff, just do like your standard panels for now, just for because it's short term.
Yeah.
Is this your house or is it an apartment?
No, it's a house, so we're renting. We just moved back to Vancouver Island, and we'll be buying in the next year or two. So it's just a rental.
Okay, well, if as long as it's rental, you can't do anything permanently in there. So yeah, so then in that case, I would recommend just putting panels on the rear wall, not whole panels, but I would do the checkerboard, and I would do it like 2x2. 2x2 seems to be the best general size. If you go bigger than that, then you have larger frequencies, but the problem is it's not nearly as efficient. So get 2x2 panels and then space them every 2 foot across, and then behind them I would put like a thin, maybe a half inch or half inch or 3/4 inch velvet curtain
Awesome.
across the back.
And then for depth of those panels, are we just going for max like 8-inch depth? Or
2-inch.
2-inch depth, yeah.
Yep. Yeah.
2 to 4. It depends on the frequency, on the resonances of the room. If you do room mode calculator, you can see what your length mode is and your width mode, and you want to accommodate that as much as possible.
I'm going to let you guys deal with that part of it. I just prefer to get in a different area.
I know it's a more basic question for you guys, but thanks for it. It's awesome to actually understand why we're doing stuff and not throw money away. So thank you.
Oh,
It's okay.
I hate to. You're in Vancouver, BC?
Yeah, that's right. Yeah, I was in Vancouver, now I'm on the island in Nanaimo. So yeah.
Oh, okay. Well, one day you have to come down and visit the laboratory. We're only an hour and a half south of you.
Oh, definitely. I'd love to see it.
Okay. Yeah. So we're down. You know where Olympia is, right?
Yeah, for sure. It's
Yeah.
beautiful.
You go to Olympia and turn right. You go out about 30 miles, and that's where the laboratory is, and we'll show you all the stuff. And there's all kinds of materials there if you're interested. I might be able to give you some materials that you can put in your place.
That sounds fantastic.
Because right now they're sitting in the room right now gathering dust.
I would recommend for anyone who's in a rental a system where you don't have to screw anything to the wall.
I would agree.
And what for your place, you have 8-foot ceilings. If you make 6-foot panels, 6 foot tall, 2 foot wide, basically, with Owens Corning 705 in it, 2 pieces, making it 4 inches thick by 6 foot, and make several of those panels and place them on the walls around until you get your decay adjusted. Now your ceiling is hard, and that's a problem. It's a low ceiling, and you may need to, like Ron says, make some 2x2 panels. They can probably be just a 2-inch thick. Now it doesn't go very low in frequency, but it will take care of that ceiling, those ceiling reflections, if you checkerboard it on the ceiling. And now that requires some holes, and you'll have to plaster and paint when you move. But
do you see the ceiling behind Jose?
Yeah. There you go.
Okay, those are great for the ceiling. Okay,
they're fantastic.
And if you're interested, I still have a number of them available. You can just have. Okay.
I think I would be visiting you real soon.
Okay.
Good stuff.
But yeah, it makes it a worthwhile trip. And to be honest with you guys, if there's any of you guys are close or want to come to my place, I'm getting rid of a lot of stuff because I'm getting old and I have to do something very soon. Because my daughter has said she will not go through my place and get rid of stuff. Not her thing.
A word on these space couplers, okay?
Yep.
You mount them directly to the surface. What will happen, as we described about the compression,
We'll talk about that now.
you'll get that trapping, but also the edges, all of those edges will diffract.
Yep. Yep.
And it will sound just lovely that way. So
Yeah.
you checkerboard those.
Yeah, I have a gentleman that lives up closer to you guys in Vancouver. He's about halfway between Seattle and Vancouver. He's got a whole studio that he built from using couplers and space arrays. And you can probably stop and see him because he's down in Marysville, I think it is. Okay.
Well, thank you very much, John. Good luck with your health, and John, thanks for your advice as well. I appreciate it so much.
No problem. Continue on because we have some other things to talk about. John touched on something, and I started talking about it earlier. We actually have two things I keep forgetting. We get moving so fast. I was talking about BAD panels.
Ah, yes.
Okay, let's talk about BAD because I have to tell you that Michael and I had a relationship that wasn't really great for a long, long time. In regard to, it was a bunch of BS, et cetera, and everything else. Because we measured it and we never got any scattering coefficient from that stuff at all, period. No matter how we measured it. Okay? What we did find was something else that we didn't expect. And again, one of the nice things about our industry is there's a lot of things that happen that we don't expect. Which means we haven't learned everything there is about sound. And one of these things is they have a very specific use. And it's not for diffusion as such. We called it for a while a targeted absorber. It was an absorber that had a bandpass on it, so you can see an amount of absorption in the center, probably around 1.2K, and it was a high peak. And people used it that way, and it was a nice thing. But we wanted to see whether we could actually get something out of it that would actually help us in that area. And what happened was I ended up having a number of these things, and I have a whole bunch of rooms in my facility that are just solid concrete. Okay, so their rooms are like 20, 30 feet, and the walls are, 5 feet of concrete in all directions. Okay, so they're like big reverberation rooms. And so if you put something on the wall, you can instantly hear what it does. I mean, it's right there in your ears. You're going, whoa, okay, that did something. Don't know what it is, but it did something. So one of the things we did is we measured the BAD panel using our new method. And what we found was there was hardly any movement other than a spectral reflection off of them until you got to around 12 to 14K. At 12 to 14K, we started seeing a whole lot of just generalized changing of phase. Not so much reflections, but the phases were going crazy. And you can separate those two in our viewer. And in doing so, the first thought was, well, I wonder if the phase differential makes a difference to our ears. So I happen to be hosting a meeting with the University of Washington Applied Physics Lab people. And they were down visiting the laboratory. And I mentioned this to the class, that we found that it made the room sound more open. Okay, that room just sounded more reverberant, even though it wasn't. And this one girl said, well, of course. And I looked at her like, okay, here's a girl who's 19 years old who's telling me, of course. And I'm going, of course what? And she says, well, from a bioacoustics point of view. And I'm kind of going, okay, that's the first I heard that particular one. Bioacoustics. Yes, you're hearing. What does your brain hear when it hears? And I'm kind of going, okay, please explain. She says, yeah. She says, the more you scramble the phase into your ear, the more high frequency spaciousness your brain perceives. And I'm kind of going, okay, explain that to a dummy. Okay. And she says, do you record things? I said, yeah. She says, have you ever used a mixing board from, I can't remember his name anymore, but he did Tascam for a while. Mackie, there you go, Mackie mixing board. And I said, what do you mean? He says, look at your Mackie board. You'll see a knob on it that says air. And I'm kind of going, yeah, I see the air thing. And she says, that is what it does. And I said, okay, so that doesn't tell me a whole lot. She says, well, how many of you play guitar? And I raise my hand. And she says, have you ever used a Fender amplifier? Well, of course. If we don't use Fender amplifiers, you know, we're real newbies. Okay? And she says, well, did you ever see something on there that's called
Presence.
yeah, presence control? Anybody here ever use presence?
Oh, yeah.
Okay. What presence does, and you have to understand, I was running a company called Ron's Keyboard Electronic Services. I used to be repair guru for everything west of Mississippi, for every kind of amplifier and keyboard there was. Okay, so I was an electronics guy. And she said, well, what it does is it boosts the presence of high frequency at around 15, 16K in the sound. Okay, it just adds a little bit of fuzz to the sound is what it does. And in doing so, it makes your mind think it's more open. And that's how your brain perceives it. And I was kind of going, so that's what presence is, that little bit of high frequency stuff. And she says, that's what air is also. It's a high frequency 16K filter that's been added to the sound. And I started going, huh. So I started looking into things a little bit. And I found out that the BAD panel added a whole lot of phase shift between 14K and 16K. And my first thought was, huh. Okay, I started listening and I started measuring the walls and stuff, and all of a sudden I realized the BAD panel was basically adding phase shift to the sound at those frequencies, which means it made the room sound bigger. Yeah. Okay?
That's what my 510 and 511 units do.
Yeah.
Measured.
So now you can actually buy these BADs and actually get some use out of them by putting them in between the absorption panels to add some presence to the room, to add some depth to the room. And that takes some of those spaces in between. Okay? I mean, you don't have to need all of them, but a few here and there will definitely help. Okay? This goes the same, by the way, with the QRDs. Okay? These QRDs, there is a certain amount of absorption that comes from them. And I got people out there telling me that Skylines and Cityscapes and QRDs all cover a very wide range of 200 hertz to 20K. And I'm looking at it going, in your dreams.
Yeah.
Okay? You can dream it till you're blue in the face, it ain't going to help. Okay? The facts are, Skylines are very restricted in what they do. And that's because the front face of the Skyline, of each of the sticks, is usually about 1.5 inches to 2 inches square. Mm-hmm. That front face is the diffusing face. It is the reflection face. Okay, what is the frequency of basically 2 inches?
Was it 6K? No, 3 to 6K, something like that.
Yeah, somewhere 3 to 6K, 3K, 2 and 3 to K in that range. So keep in mind that all these front faces are all different depths, but they're all the same size, which means they only reflect 2K, 3K, and above. That's it. Anything below that goes around them like they don't even exist, like water. Okay?
And also the size of the unit, say they're 2 foot by 2 foot, represents a face, a specular reflection to frequencies that are equal to that dimension as well.
So we can talk about that too as the next one, but I want to continue for a second here with these things. So everybody says, okay, if you make them different depths, they do different frequencies. No, they do not do different frequencies. Okay, they all do the same. They do phase change. Yeah. So you have a different timing and phase from the reflections. That's all it does. And phase change does that super high frequency stuff. So you get a burst of energy that is doing something in your Skyline at roughly around 2 to 3K, 3K, 4K in that range. And then you get another burst at around 14K. In between, it's flatter than a pancake. It doesn't do anything. Okay? So, my suggestion is, as long as you know what they are and what you can get off it, you're doing great. But if you want more than that, you have to do other types of diffusers. Okay. One of these things that we recommend, and for Mark, this is probably not for you because you're renting. Okay. But if you have your own place, John has been recommending that you take that rear wall and make it slightly convex. Okay. And the reason he's been recommending it is I recommended that to him because that's a trick we use in larger rooms as well. Okay. And that is, it will give you a slight change in phase all the way down to the size of the curve. So let's say that curve is 16 foot wide and it sticks out about 1 foot, okay, into the room. What's the frequency range of 16 foot?
Look it up. let me look at. I got a little chart here.
Yeah, there you go.
Okay.
I always go 1 foot is 1K, 2 foot is 500, 200, 250 is 4 foot.
Well, okay. 16 feet. What's it? 16 times 12 is what? I've got it in inches here. Let's see. That's 192 inches.
Which is roughly.
So that would equal 70.4 hertz.
There you go. Okay. So what it does is it gives you a 70 hertz reflection that is continually out of phase.
Broken up.
And in doing so, there's enough harmonics in there to cancel about 40% of that 70 hertz. Okay? And you can do this on your rear wall by knowing what size surfaces you have. Now, if you have something that you don't want to do at 70, you want to do something at 40 or at 20 or 30 or whatever, you just figure out what the size of that the basic curve should be.
The half wave, the half wavelength of that wall will be 35 hertz.
That's right.
And it's going to affect that 35 hertz about 10 dB down. Am I right? Is that
right?
Okay. Yeah.
Yep. So the real point here is you can use your rear wall to take care of almost everything below 100 hertz. Okay, and it only takes basically a surface. So if you have a surface that's 16 foot, that's a continuous curve, make another surface on the surface of that surface that has a 8-foot curve, or a 4-foot curve, or a 2-foot curve, and put it on the surface of the 16-foot curve. Okay, make sure you backfill all these curves with something that is very weighty, like sand. Okay, if you do that, then you'll have a low frequency converter that will kill almost everything from 100 hertz down. And it will also reduce the absorption in the room at those frequencies by probably 20%.
You can't fill it with sand. You'll have an explosive accident one day. But what I do, I'll layer 2 inches of drywall on there, and then
I would too. I mean, that was insulation. Understood. Yeah, that was understood. But yeah, I would. It needs to be
massive. It needs mass because the lower the frequency, the more energy is involved, and therefore there's more inertia you need to overcome, all this kind of stuff.
And by the way, you can use anybody familiar with something called vermiculite? Vermiculite. It's a filler that looks like cubical sections of mica. It's used as insulation.
Oh, I've seen that. Yeah. I've seen it in attics and stuff. Yeah.
Well, you can still buy it in bags. Use that as your fill because it compacts so nicely. It doesn't give you a lot of weight, but it gives you a lot of stiffness.
Oh, that's great. Ron,
and
just type that in the chat, the name of that, exactly, so I can look it up. I can recommend that. That's a great idea.
Let's see, where am I at? Chat. There we go. There's chat.
It's also used in cultivation
vermiculite.
Of plants.
Okay. Here it is. Here it is. Michael wrote it in. Thank you, buddy. I'm going to save that. Look it up, and that's a great idea. Great idea.
I have a question about that because I'm currently building one of those walls right now. I've been in contact with John.
Okay.
So So I haven't, built it or anything, but I was gonna fill it with fiberglass. So you're saying that I could use that instead?
It's actually more compact and it's more dense than the fiberglass is.
Yes, it's much more
Okay.
dense. What you
Yeah,
want in there is damping, real
yeah,
like
Right.
good damping.
yeah.
The vermiculite will do that.
If
Uh,
if if, if you can find really high density rock wool,
yeah, that does as well. Yes.
loose rock wool, not bats, but loose rock wool
Ah,
that you blow
yeah,
in.
yeah.
Okay, blow that in. Okay.
Okay.
I'm going to start
Uh,
doing that. I'm going to start recommending that. Thank you. Mhm.
these are all tricks of the trade that I've used for the last 50 years, give or take a little bit. But uh,
Yeah.
but I use sand in most of my things, believe it or not. But a whole wall, big wall like that, yeah, he might be right. But you have to use like 4 or 5 layers of quarter inch,
Yeah.
okay, and then and some really strong screws. Then you put sand in there, okay.
Yeah.
But yeah, I would use those kind of things. The higher the density is, the better off you are.
Hmm.
Okay.
Hmm.
Okay. Wow, I had not seen the chat. Curves the wall, it's a simple matter of calculator curve. Well, frequency, like I didn't catch it.
Oh,
Okay.
Sandra, on the simple manual, calculate the curve of the room. Go to my resources page, download my room mode calculator. There will be a curve calculation in there for the width of your room.
Okay.
Easy peasy.
Yeah. So you can go there. So now back to what we're talking about with those QRDs and these space curves and stuff like this. How do they absorb? Because everybody says, well, they're hard. They can't absorb anything. Okay. Well, here's how. Partially from the edges, but actually, in reality, it's spaces that do these things. So if you have a QRD and it has, let's say, vertical wells that are about 1.5 inches wide, 2 inches wide, okay, you'll see these wells with a wall and a wall and a wall, and there's a big gap inside, different
They're
depths
the
and stuff.
vertical kind of diffusers. You see the bands. You look in older control room designs with these vertical diffusers in there, RPGs.
Yeah, let me see where I can find something here. Oh, I'm not going to go bother look. I'm sorry. Never mind. I would pull it up for you, but in any case, the point is, look at the width of the wells. Okay,
Well,
there
no.
you go.
Yeah.
I was
So
trying
again,
to pull it up on my phone.
There
that's
you
it.
go. Yeah,
That's the one.
that's it right
That's
there.
it. Hmm.
That's
Yeah.
it. Okay, so look at the widths of the wells.
Sorry,
The
it's
width,
getting
the,
clear.
the width of the wells will determine the frequency at which it works best. Okay, so if it's a 2 inch well, it's going to work best at 2 to 3K.
Oh,
Oh, too right.
Let me
There we
look at
go.
that
We got it. We
exactly.
got it.
So we
Yeah.
got a 2 inch well. It is actually the full wavelength is 6.7 K. Half wave is 3.3 K.
Right. Okay, so
So
let's look at the 6.6 K, whatever it is. Okay. So the real
6.7.
point here is how does it work? Okay, and here's how to think about this for a second. If you have a let's say a high frequency device like a horn, usually you'll have a slot for the high frequency, and the sound will come out of that slot in a plane wave. Okay, yeah, it doesn't have a curve to it. It's just a plane wave. It's a little narrow thing comes out, looks like a little wall. Okay, and it's going to stay a plane wave until it reaches the flare of the horn. When it reaches the flare of the horn, friction on the edge where it touches the horn is going to slow that wave down because of friction. You're losing energy there. But the rest of that wave is going to keep expanding outward, and in doing so, it's going to form a circular wavefront. Okay, so think of it this way: it's coming out and then going like this. Okay, so it forms a circular wavefront. So now sound is basically got what we would call a circular wavefront. You know, again, none of this is real, but it's a good way of explaining it. Okay, so we have a circular wavefront. Now the circular wavefront travels to the rear wall where that set of diffusers is, and the first thing that hits that wall is the middle of that wavefront. okay? And it goes into the, let's assume we're going to narrow it down to one chamber, okay? It's going to go into that chamber, and the width of it is going to, at some point, start pressurizing that chamber, just like a piston will, okay? And as long as the outside edge hasn't reached the walls, the air will escape, just like it is in an absorber, okay? So just visualize it going in, and as long as the curve has not reached the walls, the air pressure will go out. As soon as it reaches the walls, it will seal that chamber, because that chamber is held widthwise and lengthwise. So it is now a pressurized chamber, like a resonant pipe. Okay, so now the sound is going to go in this chamber, and since it's in farther at the center, you're going to have a higher pressure in the center, which is going to push back on that curve and cause that curve to flatten out. Okay, because we're going to slow down the edges, but not the same way. So what happens is, about a third of the way into that slot, you now have a plane wave again. Okay, and that plane wave is going to seal that chamber just like the plug of a shock absorber. And when you seal the chamber, you increase the pressure in that chamber. You increase the pressure, you increase the losses, heat, conversion to heat, and that's absorption. So it's going to go all the way back to the back wall. It's going to bounce, and it's going to come back out. Okay, in doing so, you're going to have absorption and absorption going both ways, and then it's going to come back out. Okay, the point is, it's that movement in that's going to absorb that frequency. That particular unit is going to absorb 3K, 4K very, very well. You'll see a real peak of absorption here. Okay, you can use these as absorbers if you want to. Okay, you need to get a good measurement of it so you have a good idea what it does. But get a good measurement of it. You can use it as absorbers in place of other absorbers. These are targeted absorbers. Okay, so that's how these things work. Just think of it as being a well that is under pressure. Now, I'll give you an example of a large-scale use of this. 20 years ago, I had to treat the hangar deck of an aircraft carrier. Now, we're talking something like the Nimitz, okay? And it's a big hangar, very big hangar. And the problem is, it's made out of steel. That's it. There is nothing in that hangar deck that is burnable. We don't want anything burnable. Catches fire, everything burns. So it's all steel. So it's like a big, huge echo chamber. And the problem was that you talk, and you couldn't understand anybody. So when they made announcements like, little speakers, there were 3-inch speakers on the wall, abandoned ship, fire, etc., nobody could understand them, so people died. Okay? So the question that came to me is, how can we make it understandable in there? Well, I said, you put a whole bunch of fiberglass. No, you can't put fiberglass in there because that'll absorb the fumes of the jet fuel and stuff, and it'll be explosive. So nothing that is porous. And I'm kind of going, well, it has a whole bunch of other things. How about diaphragmatic? No, can't do that because there's air behind it. You can't trap that. Okay? And I'm sitting there going, okay, I don't know. Let me think about this one for a while. So I did what I'm doing right now with Jose's place. I'm looking up at its ceiling, and I see these long I-beams that are roughly 10 feet thick going down the length of the flight deck. And there's a big 10-foot space inside those things. And my first thought was, well, that's one hell of a big diffuser, And I thought, well, if you take them and you put weld panels in between the different lengths, you can divide those long 700-foot wells into, everything from 2 foot up to 20 foot. Okay, and that would make little wells like you have on your ceiling right now. Okay, and then if you cover those wells with another plate across the top of it and leave a gap in it, so you have a Helmholtz resonator, now you have a big Helmholtz resonator. Okay, and each one is a different frequency because they're all different sizes. Okay, and when it was all finished, that's what we did. We covered the entire ceiling with sheet steel and left 2-inch or 3-inch or 4-inch gaps at each end of each well. And we had a series of wells that covered everything from roughly 25 hertz all the way up to 20K. and it sucked down the reverb time of that room from roughly 8.5 seconds down to 2.5 seconds. It became usable, okay, with a really good speaker. But this is what thinking outside the box means. You know, look at what you have and look at it from a physical point of view and think, what can it do to sound? Under what conditions? Okay, so in your case, you know, you can make walls that do the same thing. Have you ever thought about making an absorptive wall out of hardwood, the slots? That's one way of looking at things. Okay, if you want something that's really sexy looking, that gets very sexy looking. Okay, you know, anybody ever seen the recording room that is done by what's his name? That has all the cityscapes with the sticks out 6.5 feet.
Yeah. Blackbird.
Yeah, Blackbird Studio.
COC.
Okay. Yeah, and the real point is, he's got so many sticks sticking out in so many different directions that there's nothing can reflect anywhere. Okay, but it's all done at high frequencies. Low frequencies got stuff behind those things, and people don't know that. They don't know there's fiberglass behind those things. There's all kinds of things behind that stuff, but then you only see the surface because it's very attractive. You always look at what looks good, because behind it, it's just plain old physics. Okay, and anybody can do that. All you guys can do that too. None of physics is complicated. If you can do basic algebra or basic addition and subtraction, you can do physics quite nicely. All you have to do is keep in mind, it is the study of how the physical world works. That's it. That's all it is. It's nothing, there's nothing magic about it. It's easy. It's very easy. But you got to think that way. You got to think in physical sizes. You got to think in spaces, stuff like that. Okay? So now, let's see. Curved wall, vermiculite, harmonic damping. I think we just talked about that somewhat. The fact that if you take that rear wall and you make it different sizes, you now take harmonic damping into place. You've done 70, you've done 35, you've done 140. Remember that for every curve or everything you have, there is a higher harmonic that is going to be affected by 50% or 20% or 30%. So when you fix something, you're also going to fix other things that may not want to fix. Okay, so be careful with what you're doing.
That's why
Okay.
I caution the use of Helmholtz or resonating type traps, because you really have to know what you want to do and what this unit that you're building will do. So
and what you want to do a lot of times is you want to make sure that whatever you're doing is at the highest frequency you're concerned with. Not the lowest frequency, at the highest frequency. And the reason is because the higher frequencies don't affect lower frequencies near as much as the lower frequencies affect the higher frequencies.
Right.
Okay, so work your way backwards. It's easier. Okay, then you can treat your room, you know, frequency by frequency. But never work your way up from the low frequencies upward and try to treat it, because everything you do is going to have a knock-on effect to all those low frequencies. Okay. So I'm trying to see if there's anybody here that has any other questions. I think we're already past the quitting time already by half an hour. So is there any other questions you guys have you didn't get answered?
I had a question about the checkerboard, you know, spacing out the 2x2 panels.
Yep.
So if I'm looking at the chart that you guys had, you know, a 4-inch of 705, let's say around 80 hertz, it was around 0.9 or so.
Mm-hmm.
If you do that checkerboard, you know, sequence, does that 0.9 go up?
Oh, yeah. It goes to about 1.7.
Okay. And then the follow-up question to that is, if 0.9 is close anywhere, what is that, like 6 dBs to 8 dBs or so?
0.9 is 6 dB, 0.99 is 8 dB,
Okay.
0.999 is 10 dB.
Now, and in that case, what is the 1.7? What would that be?
I think we measured it in attenuation. It was something on the order of around 20, 22, 23.
Wow.
Yeah.
Okay, so then it's a giant difference to have them spaced out.
Yeah. Well, it's an exponential scale. So just take the 0.99 and look at it from the exponential 6 to 8 to 10 and continue upward until you reach that
Right.
number. Okay. There is you can put together an Excel spreadsheet that does that.
Right. Okay.
Okay. And that's why we're going to be measuring these things on the Gobo, so that we can sit there and say it has this kind of attenuation. Period. Okay. Then you can compare it against the 0.9 and see how they relate to each other. And this will
Gotcha.
be actual measurements rather than guesses.
Okay. Much
Okay.
better.
So that'll be all coming probably in the next 6 months. We got a lot of testing to do. I've probably got 3-4 weeks of testing to do. And then we have to transfer it all to data and then put it in charts and figure out how to best display it and then recalculate it back upon the other measurement and see if we can get a coordination between those two. That's right now, that is the magic number that everybody has been searching for almost 100 years now.
Yeah.
Is how to convert a dB scale to a coefficient of absorption, or to a what do you call it? That's the word I'm thinking of. None of these are coefficients. You have to understand coefficient is an invented thing for us to say, okay, it goes only to 1.
Right.
Okay. Whoever did that, and I can tell you that was Dr. Paul Sabin that did that. He got called out on it the same year at the ASA. Okay. One of his contemporaries, who was very well known as well, basically said he was an idiot. But by the way, just so you're aware, we are gentlemen compared to what they were back in the 20s. Okay, we don't call anybody a flaming idiot. Okay, we try to be more gentlemanly. We may say, you need to take a flying whatever. Okay, but we don't call them those weird names anymore. Okay, back then they did it right on their papers.
Oh.
It was like I read that paper and I was like, well, that's rather interesting. Calling me a real idiot. So
Question.
yes.
I'm sorry, I got a question by Michael. He says, he asked, does the edge effect theory work the same below 100 hertz?
Yes. Yes, it does. It goes, as long as you have, as long as you have an edge that is long enough or wide enough for it to be seen, it will still give you a certain amount of absorption at that point. Okay.
Depends on the length of the edge, the depth of the thing, and many other factors.
Yeah. Now, one of the other things to keep in mind is it seems to be that the thickness of the material determines where the peak of the absorption is. So 1-inch material had a peak at roughly 1200 hertz. 2-inch material had a peak at around 600 hertz. 4-inch material had a peak at around 350, 300 in that range. And 6-inch, I think 8-inch material had it roughly at around 125. So it is not an equal amount of addition. It peaks at a certain frequency and it goes away lower and higher both. Okay, so if you look at 2-inch, there is hardly any addition at 125 hertz at all. The only time you get that is if you get deep enough to have a material that's 125 hertz. Okay, so that I would imagine would be 8-inch, 12-inch material.
Okay. I'm sorry, sir, I can't say your name. Quargabach? Asked about compiling data. It takes weeks to compile data because we are testing. We're waiting for these tests to be done, and we have to wait, and then we have to correlate all the information and make charts and all that kind of stuff. So
first we have to calculate the numbers.
Give us some time. It takes quite a bit of time and effort.
All of our clients always ask us, how long before we get the answers? Well, the test only takes 20 minutes. How long to get the answer? If I did nothing but work on that particular project and that particular day, it takes roughly 3.5 to 4 hours to calculate all the decays, turn it into a decay number, and then go into it and convert that to the number of Sabins, et cetera, the whole thing. So there's a whole lot of 20 minutes of basically computer time just calculating numbers.
Yeah.
And then we have to convert them all and put them inside of Excel spreadsheets, and we got to calculate those backwards and all kinds of stuff. So it takes quite a while.
Yeah.
Mike, you wanted to know bass mods. Okay, 6 inches, 6-inch bass mods. How many of you know about bass mods? Okay, bass mods are produced by a company called Real Acoustics. They're made specifically for certain frequencies. Richard Lenz has probably done more for low frequency absorption than anybody in this industry has. He and I have worked together on these things. I've got probably 4 years worth of research along with him. The latest version he has, he's pretty well stamped it down that he's the guru of low frequency absorption. Okay, I will tell you this much: if you have a bass mod that is 4 foot wide, the next bass mod can't be closer than 4 foot. So you put them along a wall, you stand them up, and if they're 4 foot wide, the next one will be 4 foot away.
At least.
At least that much.
Yeah.
Okay, that's the minimum.
They will interfere with each other otherwise.
Oh boy, will they? And I don't recommend it, by the way, because the interference between them is completely unpredictable. I can tell you right now that putting them in the corners is probably the worst thing you can do. Make sure you're at least 4 foot out of the corner before you put the first one there. Okay? Because anytime you go in the corner, now you have 3 different wavefronts at different frequencies. And they're all impinging on that diaphragm. And it's like, having 3 different drum beaters hitting the diaphragm at different places in different ways.
Yeah.
And the diaphragm just goes, oh, okay, I'm not going to give you anything that you can make any sense of.
I think it was.
Ron, it's
I
the
think it was
same
last-
thing.
I'm sorry. Go ahead.
Yeah, Ron, same thing, not in a tri-corner, but a bi-corner, like a wall ceiling or a wall floor intersection.
Yeah, any intersection like that is a no-no.
I would avoid it. Yeah. We recently did a
4 foot minimum.
Well, it's for if your absorber is 4 foot. Okay.
Yeah.
If you have
Assuming
a 2 foot,
that for the conversation.
right. If you have a 2 foot wide one, then 2 foot.
we recently.
Well,
did
you might have a 4x8.
studio.
So are you concerned about the 4 foot dimension or the 8 foot?
Well, it depends
Michael.
on which one's standing up.
Yeah.
Yeah, 4
Michael,
foot tall. Yeah.
If it's 4 foot tall and they're 8 foot long, then they should be 8 foot apart.
Sure.
Okay.
Michael recently did a mastering room in Oslo, Norway, a year and a half ago. We used 2 bass mods, one in the center, the front wall, and one about a third of the way up from the back wall on one side only, and that's it. That's all it needed, and it was just tighten that right up.
Okay. Thank you.
Yeah, you
Okay.
keep them away from each other.
Yeah.
Like the song goes, you got to keep them separated.
I got
Yeah.
a question about that because I have a couple of the 3660s now. Those are those triangular ones, and I ended
Yeah.
up getting them before I found out about the whole putting them in the corners.
Yeah.
So
Put it in the corner, okay? But
Mhm.
only one. Don't stack them. Don't put them next to each other. Don't try to get 3 or 4 of them in the same area.
Right.
Just put one in there. That's it.
one, because so I have 2, for example, so it would be one on each corner.
Yes, and put them at least their normal height above the floor. So if these
Okay.
things are 4 foot high,
Yeah.
60 inches, aren't they?
Those are 60 inches. Yeah.
okay.
that's why I
So
said-
make sure the bottom of the one you put in the corner is 60 inches off the floor.
Okay.
Okay. You
Okay.
want it away from the floor, away from the ceiling.
Yeah.
Okay.
Yeah.
Okay.
The less interactions you have, the less unpredictability you have.
Yeah. Yeah.
Gotcha.
Now, what you get is going to be a combination of the length and the width tone dynamics. So they're going to be probably a dual peak, depending on which one has more power. And that's what it'll be. I mean, there's no way around that. We
Yeah.
can measure it for you and tell you exactly what it is. then you know where to put it. But if you're going to put it in the corner, then you're going to have to deal with a dual peak. Both peaks will be down around 6 to 8 dB.
Gotcha.
Okay. So it'll be a wider peak. They'll be fairly close together. Well, it depends on your room dimensions.
Right. Okay.
Mike, does that answer your question too?
It does. Thank you.
No problem. If you guys ever want to,
Just as a sort of a sidebar to this, I'm thinking, medium large room application, not studio size application for the bass mods in the 3660s.
yeah, and
Same scenario, right?
actually, that's probably a better scenario. Yes.
It is. Yeah.
Yeah. I
In terms of the minimum spacing.
Yeah.
Yeah.
I use them for large concert halls and stuff, and that's the minimum spacing. I just pick a wall.
I'm working on a jazz club right now where I'm specifying some of those.
Oh yeah, well that'll do it. Just pick the longest wall that you have access to, and just put them flat on the wall, flat on the floor in the situation.
I think I have some opportunity on the wall.
Yeah. Just make sure you have that space. Personally, what I would do is I would start in the middle. I put one in the middle, and then I'd start spacing. A 4 foot out from that.
Yeah, I don't. I don't have the luxury of putting them just anywhere I want. So.
Yeah. Just pick a spacing. As long as they're at least 4 foot apart, they will operate like they should, and all of them will operate at the same frequency.
Yes.
Right.
Okay. But I can tell you right now, they work really, really, really well. You don't need very many of them. We've done a church that sat 2,000 with, I think, 6 of them. So
say that again?
I said we did a church that sat roughly 6,000 people.
Oh.
And we only used 6 of them along the rear wall. That was
Got it. Okay. Yeah.
Yeah, they're very efficient.
Thank you.
No problem. If you guys, by the way, if you guys, you're here, I give you the same thing I give everybody, but I'll give you extra here. If you ever need to reach me, you can either reach me this way here in Zoom, or you can call me at my number. Okay, I have no problem at all answering those questions. Okay, I spend a lot of time with people on the phone because, like I said, I'm 78 years old. I want to make sure that everybody gets educated because there's nothing worse than having people that are uneducated and they could get educated. It's easy to do.
Yeah.
Okay.
I'm going to put a plug in for our acoustics course here.
Yeah.
We're doing an acoustics course.
And it's going to be a lot more detailed than this is. So, I will say this. There's 3 sections to it. One section is acoustic theory, and it has to do with physics, pure and simple. Okay? It's 10 lessons. If you don't want to get that deep into pure physics, then they also are going to be a section that is going to be on small room acoustics and large room acoustics. Okay?
We're going to talk about all the different kinds of absorption, how they work. As we've discussed here, we'll get into it in a little more detail. Show it.
Yeah, Mark. Mark, if you want my number, let me give you my home number. Okay, where I'm at right now. It's area code 360-915-9159. Anybody wants to talk to me, they can call me that number. Just, keep in mind, I keep weird hours. I'm usually up almost all night long, usually. Every once in a while I'll sleep, a couple times a night, but most of the time I'm usually up from about 1:30 in the morning until about 8 o'clock in the morning. And then I sleep for a couple of hours. My wife says I live vampire hours. So, but I'm willing to help anybody who's interested in giving me a call. Just, knock it up. Okay, but anything else to see interested? Thank you. I have a bit of an idea now. Your base mods with oh yeah. If you want to do it on a poly wall, don't worry about it in this situation. Pick the base mods are picked by frequency. It doesn't really matter what wall they're on, as long as it's a fairly flat wall, and as long as you can put it right against the wall, it's happy. So I wouldn't do it on a 2-foot curve, okay, because it'll probably stick out. You don't want any gap behind it, any space behind it. But if you have like a 16-foot wall like you have, you could probably put one in the center and probably one on either side, and going out over the curtain type thing. But to be honest with you, in a room your size, one in the center will probably do the job.
Absolutely. Oh yeah.
Yeah.
You'd be surprised how much. Yeah, a lot.
Yeah. Michael, Booker, does that answer your question? I know you're there. Oh no, like they left. I was thinking about more of the sidewalls. Same thing. Doesn't matter. As long as you have enough room to put these things 4 feet. Well, if you have 4 footers, make sure they're 4 foot apart, and nothing goes in the corner closer than 4 foot. That's all you have to worry about. For a room,
you'd be surprised and impressed how much these things will do.
Yeah, if you're working if you're doing a recording room of any kind, I guarantee you 1 or 2 of these will do everything you need to do.
Right.
Yeah, I've actually treated whole recording rooms with just 1 unit.
Yeah.
Yeah.
Would that be someone that I could use in my space, or would that be it, and then I could transport it when I move? Would that be okay for me?
Oh yeah. Yeah.
Yes, it's possible, but then we get back into the talk about harmonic damping of just regular force absorption.
Well, find out what all of your modes are and what your the audible harmonics are.
Yeah.
Run a frequency response of the room.
Yeah, and when we talk about performance spaces or mixing rooms, these are small rooms basically. Don't have an RT; they have a decay, and we do not hear linearly. We need elevated bass levels so that we can perceive it as being flat. So a lot of times you can overtrap that bass, and it'll be too thin sounding in the room. So
look at your curves. Oh God, I hate you, Noel.
Do a room sweep.
Well, but I'm saying look at the curve, the Fletcher-Munson curve. Okay, in order to be able to hear low frequencies, it recommends an increase of low frequency of about 6 dB, between 5 and 6 dB per octave after 250 hertz.
Yeah.
Okay, and a decrease of around 5 dB above 4K. Again, the same situation for every octave.
Nice little roll off.
Yep. Okay, that's probably close to an ideal. Everybody has their own ideal what an ideal is. I'm just trying to tell you what the general consensus is for what they call SMPTE. So if you're familiar with SMPTE, the Society of Motion Picture People, if you go see a movie or go to a movie theater, it's going to be a SMPTE curve.
Yes, and if you can control the decay in your room to kind of match this kind of curve, it will sound natural.
Yeah.
To we humans that inhabit these spaces.
Yeah, it'll sound very much like if you're outside. That's the whole idea. You want just a little bit of a boost at the low end because, I'm sorry, our ears are
we can't hear.
Lousy. Yeah, right. If you're me, you're lucky if you could hear, from roughly 250 hertz up to around 4K. But is there any other questions? I see all kinds of things here. By the way, Quarterback, we're probably not going to do the book right now. This course we're doing is going to probably take the place of the book for all of us because we're all too lazy to write a book.
Not too lazy.
Yeah, we are.
It's hard.
That's what I said. It's too lazy. But yeah, the video will be about 30 sections long, and it will basically compile what John and I both know into one set of courses. It'll probably divide it into 3, so you don't have to buy the whole thing if you don't want to. I think
we changed it, Ron. We changed it. What it's going to be? It's going to be a monthly subscription.
Oh, cool. Okay, well, whatever it takes.
So they can get anything and everything they need.
Okay.
This is our life's work, guys. This is Ron and I, our life's work, and we're putting out to the next generation of acousticians and designers, and people, or just engineers who want to know, inquiring minds.
Yeah. Used to be I was worried about making a lot of money. To be honest with you, I've never done that. I'm poor as a church mouse, you know, and anytime you have a laboratory, you're even poorer.
Yeah. Anybody know any rich teachers?
Yeah. Or how about rich laboratory owners?
Oh my God.
By the way, just so you guys have, I'll put it out there where you guys are, and I'm sure none of you are interested, but if you ever hear of anybody who wants a laboratory, please let me know. Because I want to teach somebody to take over the laboratory so I don't waste all that money and all that time creating something that's only one of a kind in the world. Okay? So you have to
I'm still working on buying it from you, buddy. Really.
Well, like I said, I always tell people, I'm not looking for a big chunk of money. What I'm looking for is an income. Okay? So if somebody can guarantee me $7,000 a month or $8,000 a month, I'll be happy to train them and they can come in and take over. You know, so, you know, who knows? Maybe one of you guys will be a laboratory owner. Then you can become the guru. Meantime, I think we've gone way over our time. Alrighty. Anybody other questions?
I had one more question.
Sure.
I had John had explained to me that you can only get 10 decibels of absorption per wall. Is
per surface contact. Per material, per surface contact. You can get a lot more absorption, of course, but that's like what we've tested per surface contact and the average.
Let's make sure. Yeah, let's make sure. Remember the old saying, it all depends?
Yeah.
Right.
Yes.
Okay. If you're using the coefficient of absorption as it is written today, that's the maximum you can get.
Right.
So it's 0.999 is 10 dB.
Right.
Okay. Now, in reality, you can get more than that, because we know the edge effect is going to give you more. Okay, but I have to make sure that there's that little disclaimer on there that says if you use the coefficient of absorption as it is described today, that's the maximum absorption you can get on any surface.
Yeah. And that's why we're doing this research now. That's why we're doing all this testing. Yeah, we're trying to work this out.
And Sandra, I can tell you right now, we've already figured out that it can be shipped to Indonesia, so definitely Oslo, Norway. I can. In fact, I spent some time up there in Copenhagen at the DTU, and we were talking up there for a while. But their comment is, "Well, do you come with it?" And I'm kind of going, for a certain period of time, I do. After that, it'll be like, call me on the phone. I'll be in Hawaii then.
He does really good remote testing, Ron does.
Yes.
No
yeah.
problem.
By the way, just so you're aware, anything you guys need testing done, I can do remote testing from anywhere in the world. I just need a person there to move the sample. That's it. And I have a couple of people to do that. So I've done, my system is set up so all 12 of my computers all talk to each other over the internet. And I can run any computer any way I want to, including all my testing. So it's just a matter of pushing a button and say, okay, I want to do an absorption test, click, and we want to do it this way, this, and here we put the thing and move it over and push the button and it tests. So this can be done, remote controlled. Okay, but to be honest with you, I like going in and talking to my clients. It's a lot more fun. All you have to do, guys, is imagine coming to my place and sitting down, and we can talk for 8 hours doing nothing but talking. Okay, believe it or not, about 90% of my customers say the reason they come is because they can just talk. That's it. They said they learned so much doing that, building new materials and stuff. But yeah, I was hoping it would be a real proposal, Sandra. But if you manage to find somebody who's interested, let me know, okay? Or if you are yourself, okay? But in the meantime, anything else from guys? Oh God, I've got to get ready to go to a meeting myself here in a couple minutes. I got another client that I got to meet at 10 o'clock. So, okay. So we will see you guys later. Thank you for coming to this. And we're going to do this again probably about a month from now. I think John and I have been talking about trying to do one of these every month. And just if you have any questions, please put them on that Facebook page. Or ship, that way we have a bunch of questions that we have ready for us when we get in here, and then we can have all kinds of paperwork and stuff to show you guys, how this thing really works. Okay.
Okay.
Alrighty, gentlemen, have a great day.
Thank you, guys.
Or evening or whatever you're having right now. Be good. Talk to you later.
Okay.
Thank you.
See you.
Okay. Bye. Bye.
Okay, goodbye.
Bye. Talk to you soon.
Okay.
Goodbye. Ciao.